I'm going to discuss topic in data structure tree, unit 4, tree data structure. So let's discuss about tree, unit 4th. So the basic definition of tree, what is tree? A tree is one of the data structure. As we all aware about the syllabus of data structure, we have different data structures used to store data. We have linked list, arrays, we have graphs, also we have tree, one of the data structure that represents hierarchical data. So where we want to store hierarchical data, we use tree as a data structure to store data and to perform operations in the data. Suppose we want to show the employees and their positions in the hierarchical form, then it can be represented as shown below. Employees, different employees and their positions, like John is the superior, then Steve and Rohan, and this is the hierarchy of employees in a company or in a organization. And this particular structure, a logical structure, it is a logical structure, it is not a physical structure. So it's a logical structure, is known as tree. And this structure is similar to the real tree, so it is named as tree. But there's a difference between a real tree and the logical tree. In the data structure is, in the real tree, a root is at the bottom, leaves are at the top. But in this tree data structure or the logical hierarchical data structure, root is at the top and the branches are moving in a downward direction on the backward or lowerward direction. Therefore, we can say that the tree data structure is an efficient way to store data in hierarchical way. So wherever there is a need of storage data in the hierarchical form, we use tree. Next. Example of tree. As we all aware about this, like this, and it's also a tree. So a tree defined as a collection of objects or entities known as nodes. It's a collection of entities known as nodes. These are the entities known as nodes, and they are linked together to represent the or simulate hierarchy. This is a tree data structure is non-linear data structure because it does not store in a sequential manner. Data does not store in a sequential manner. Data is stored in a hierarchical order or non-linear order. So it's a non-linear data structure. So data are stored in a multiple levels. And the topmost node is known as the root. So this is the root in this hierarchy of employees, and the top node is known as a root. And each node contains some data, and each and every node contains some data. And data can be of any type. Data can be of any type. It can be alphabetical or numerical data, or any kind of data. So the data type of data would be a string here. So we can say it's a tree data structure, and each node contains some data. Each and every node contains some data, and the link or reference of other nodes that can be called children. So data in a node and the reference to nodes also called as childrens of the particular node. Again, we have a tree where this is the root of the node of the tree. It is the topmost node in the tree hierarchy, or we can say the root node is the one that doesn't have any parent. So root is the parent of all the nodes in the tree, or it doesn't have any parent. And in this structure we have one without any parent or the parent of all these. So node number 1 is called the root of the tree. And if a node is directly linked to some other node, it would be called as parent-child relationship. So a node that are directly connected to a node, so 1 is the parent of 2 and 3, so parent-child relationship. So we can say a child, so 2 and 3 these two nodes are the child of one, or we can say if the node is a descendant of any node, then the node is known as the child node. Descendant node is called the child node. Parent, if the node contains any subnode, then that node is said to be a parent of that subnodes. So 1 is the parent of 2 and 3, 2 is the parent of 4, 5 and 6, 3 is the parent of 7 and 8. So this is called the parent. If a node contains any subnode, then that node is said to be parent of that subnodes. Siblings. What is sibling? The nodes that have the same parents are known as siblings. So in this case, 2 and 3 are siblings. 4, 5 and 6, these are siblings. 7 and 8, these are siblings. So these are siblings. Another terminologies is we have, so we discussed about the root, what is called root. So root, we have a child nodes. We have discussed parent. So a root is different from a parent. We have sibling, children of a same parent is called siblings. Then we have leaf node. The nodes that doesn't have any child node is called the leaf node, and a leaf node is the bottommost node of the tree is called the leaf node, bottommost node, and doesn't have any children is called the leaf nodes, and also called as external nodes. Leaf nodes are also called as external nodes. So here in our tree we have 8, it doesn't have any children. We have 11, it doesn't have any children. 10, 9, 4 and 6. So these all are the leaf nodes. So we can say these are the leaf nodes. It doesn't have any children, so called leaf nodes. Ancestor node, another term we can say ancestor node. So we can say ancestor node. What are the ancestor node? Ancestor node of a node is any predecessor node on a path from the root to that node. The root node doesn't have any ancestor because we don't have any path upward to a root node. So in the tree, as shown in the above, this tree, the nodes 1, 2 and 5, 1, 2 and 5, these nodes are the ancestors of 10. So ancestors of 10 are these nodes 5, 2 and 1. If we talk about the 11, so ancestors of 11 are 7, 3 and 1. So this is called ancestor node, or the predecessor node from a path to that particular node. Also we have descendant. The immediate successor of a given node is known as descendant of a node. In the our figure, 10 is the descendant of 5, 10 is the descendant of 5, 11 is the descendant of 7. So this is called descendant. So we discussed all these terminologies: root node, child node, parent, sibling, leaf node, ancestor node and descendant. Next, what is the implementation of a tree? Also, we can discuss about the terminologies, basic terminology. Tree is a recursive data structure. Number of edges if there is a n nodes, then there would be n minus 1 edges. So if n node, so here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 nodes. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 edges. So this is called number of edges in a tree. So number of edges is 1 less than 2 number of nodes in a tree. Depth of the tree. Depth of the tree represents as the root is having depth 0, and the descendants of this one root node, 3 is having 1 depth, 8 is having 2 depth, 11 is having 3 depths, 1, 2, 3, 3. So this is called the depth of a node X. Depth of 11 is 3, depth of a node X 7 is 2. So this is called the depth of the tree. Now we will cover this implementation of tree, how to implement a tree. And a tree, our data structure can be created by creating the nodes dynamically. We can create nodes dynamically with the help of pointers. So we use pointers here, creating nodes dynamically. The tree in the memory can be represented as shown below. Tree in the memory can be represented like this. Integer data, the data that contains the data, the left node value and the right node value. This is called structure, programming structure of a tree. Like here we have a hierarchical structure, a tree, in which A, a root, B and C, then D, E and F. So is a pattern. So A, integer data. So data here is A. Left child or left pointer is contains the address of left node. So here it contains, with the help of pointers, A contains the address of left child B, and this portion, third portion, contains the address of the right child, it's C. So this is the programmatical structure of a node in a tree. A tree contains data, also the addresses of left or right child. If exist, then the address; if not exist, then the values will be null. So in the above structure, the node contains three fields. The second field stores the data. The first field stores the address of the left child, and the third field stores the address of the right child. This is the simple architecture of implementation of a tree. Then basic tree, a binary tree. Binary means 2. So the binary tree means the node can have maximum 2 children. A node can have maximum 2 children is called a binary tree. Here binary name itself suggests that 2. So we all are aware about the binary meaning of our word binary. So 2. Therefore each node can have either 0 or 1 or 2 children. So a node can have 0, it can be a root single node, or it can be a leaf that contain any node, 0 children or 1 children or 2 children. So this is called a binary tree. And the properties of binary tree: at each level of I, the maximum number of nodes is 2i. Each number of label I, maximum number of nodes is 2i. This is 0 level, so maximum number equals to 1. This is 1 level, so maximum nodes will be 2. This is second level, so maximum number of nodes will be 4 if it is contains, so maximum 4 nodes. So this is the concept of maximum number of nodes in a binary tree, 2 power I, where I is the level of the tree or a particular node level. And the height of the tree is defined as the longest path from the root node to the leaf node, longest path from root node to the leaf node. the tree which is shown above have a height equals to 3. This tree is having height 0, 1 and 1, 2 and 3. So this tree is having height 3. Therefore, the maximum number of nodes at the height tree 3 is equals to 1 plus 2 plus 4 plus 8 equals to 15. So this is called a binary tree. Also, there can be a representation of a binary tree in a single or one-dimensional array. Suppose we have a binary tree like this. We have A and we have children of A, B and C. Then the children of B is D. Again the children of C, suppose we have children of C like E and we have F. Suppose we have these, and when the data of the tree is stored in an array, so the data of the tree, if we store it in the array, so the 0 position, the 1 position and 2 and the 3 and 4 and 5 and 6 and 7. So we have A here, then we have B at the position of 2 and we have C and D at the position of 5. We doesn't have any node, and here we have E and F. So why I just put in these numbers? So location of a number 0 of the array can be used to store the size of the tree of the total number of nodes, and all non-existing nodes are represented by this /0. Non-existing nodes are represented by /0, and index of the left child of a node I is 2i. So A at the 1 position, 2i, 2, 1, 2, C, 3. So these are the representation of a tree, binary tree in the one-dimensional array. Now comes to the types of binary tree. We have many types of binary tree, and we will discuss only these few types of binary tree. First is full binary tree, or we can say proper binary tree, or we can say strict binary tree. So a full binary tree is also known as strict binary tree, and the tree can be only considered as the full binary tree if each node contains either 0 or 2 children. So each node contains either 0 or 2 children. So if we have this example A, B, C, we can say it's a full binary tree. Each node is having 2 or 0. So this is having 2 children. These 2 nodes are having 0 children. Or we can say this example where B is having 2 children, D and E. It's also a full binary tree. So the full binary tree can also be defined as the tree in which each node must contain 2 children except the leaf nodes. So except the leaf nodes, all nodes contains 2 children. So these are the 3 leaf nodes D, E and C. Except these A and B contains 2 nodes. And properties of full binary tree: the number of leaf nodes is equal to the number of internal nodes plus 1. Here we have number of leaf nodes equals to number of internal nodes plus 1. So here we have 3 leaf nodes and the internal nodes are A and B are internal nodes. So we can say plus 1, internal node plus 1. If we add another here, so the leaf node will be 4 and the internal nodes will be 3. So 3 plus 1, 4. So this is an example of or properties of a binary tree, full binary tree. And the maximum number of nodes is the same as the number of the nodes in the binary tree, like 2 power h plus 1, height plus 1, to 2 power h plus 1, h plus 1 minus 1. So this is the height, maximum number of nodes in the full binary tree, and the minimum number of nodes in a binary tree equals to 2 to the power of h minus 1, and the minimum height of the full binary tree is log 2 n plus 1 minus 1. So these 3 mathematical formulas. First one is maximum number of nodes in a binary tree, minimum number of nodes in a full binary tree, and the minimum height of the full binary tree. So these are 2 or 3 mathematical concepts: full, maximum, minimum, and height of the binary tree of any tree. So we can calculate n number of nodes. So we can calculate if the depth of the tree is very large and we have thousands or millions of nodes. So we can calculate the number of maximum, minimum, and the height of that particular full binary tree with the help of these formulas. Now, second point, a complete binary tree. A complete binary tree. Then we have a complete binary tree. The complete binary tree is a tree in which all the nodes are completely filled except the last label. All the nodes are completely filled except the last label. In the last label, all the nodes must be as possible as left. In a complete binary tree, the nodes should be added from the left. So what is called a complete binary tree? So if we say this is a complete binary tree, a complete binary tree, again a complete binary tree, again a complete binary tree. So the definition of complete binary tree: the complete binary tree is a tree in which all the nodes are completely filled except the last label. Except the last label, all nodes are completely filled. These are the last label, all nodes are completely filled. In the last label, all the nodes must be left as possible. So this is the last label. So this is the left node. Again, it's also a complete binary tree. But if we can say like this, it can't be a complete binary tree because we must fill the position of 11 at the position of left child of 5. So it violates the property of complete binary tree. So it's example of a complete binary tree. And the maximum number of nodes in a complete binary tree is maximum number of nodes in a complete binary tree, and the minimum number of nodes in a complete binary tree is h. Maximum number of nodes, minimum number of nodes, and the minimum height of a complete binary tree is this is the minimum height of a complete binary tree. Next, we have a perfect binary tree. Next, we have a perfect binary tree. A tree is a perfect binary tree if all the internal nodes have two children. If all the internal nodes have two children and all the leaf nodes are at the same level, it's called a perfect binary tree. All the internal, this is a perfect binary tree. This is a perfect binary tree. This is not a perfect binary tree because these nodes are not at the same level. All nodes are not on the same level. These four leaves are at this level and these two are at a different level. So this is not a perfect binary tree, but it's a perfect binary tree. So in a perfect binary tree, all the internal nodes have two children and all the leaf nodes are at the same level. So this is an example of a perfect binary tree. Next example or next type of binary tree, we have a degenerated binary tree. A degenerated binary tree, and degenerated binary tree is a tree in which all the internal nodes have only one children. All the internal nodes have only one children, like this. This is having only one children, one children, one children. Internal nodes are having one children, one children. So this is called a degenerated binary tree. All the internal nodes are having one children, like this, this. These two are the examples of different degenerated binary tree. Next categories of binary tree, or we can say in our discussion, the last category of binary tree is balanced binary tree. And in the case of a balanced binary tree is a tree in which both the left child and the right child differ by at most one. Left child and right child at most differ by one. Like we can say ABL tree, red black tree are the balanced binary tree. So we can say this is the example of a balanced binary tree, at most one variation. So these all are the categories of trees, types of trees: full tree, polystyric binary tree, complete binary tree, perfect binary tree, degenerated binary tree, and we have balanced binary tree. Thank you.